Thanks a lot. I'm excited to talk with you all. I'm Ben. I am officially, I'm employed by LightStep, which is a company working on distributed tracing, but I'm spending most of my time on OpenTracing, which is, if OpenTracing is like a really vibrant thing in 5 years, I would be so happy. I think it's a really important project, and I'm really here to talk about OpenTracing right now and not about LightStep, although they can be confused sometimes, but they're really not the same thing. So OpenTracing. All right, so microservices, they're a buzzword. Everyone knows the gist of it. I think they're here to stay conceptually. The idea of deploying one giant monolith that incorporates, the work of hundreds of engineers is so unwieldy for so many different operational reasons, certainly for computer scientific reasons of scale, but also just for CI/CD kind of reasons. A lot of people are breaking their systems into pieces. I honestly don't think it's necessary for them to be micro. Micro to me means 1/1,000,000th. I mean, I think, 1/12th a service would be, enough for most companies, but that sort of direction is where our industry is headed, and I don't think anyone is really looking back who's gone in that direction. And it's generally a good thing. That said, when you decouple your system into small moving parts, your monitoring almost certainly breaks as a result. The way I would illustrate this, if this blue square is your monolithic application, and these are the libraries that were in your monolithic application, your microservice might have one service roughly for each component, whether it's doing authentication or if it's handling image resize queries or whatever thing you decide to split out. And that's fine. However, monitoring used to be a matter of just logging the request as it propagated through your process. And monitoring is really about telling stories. That's good monitoring, and good metrics should be about telling stories about systems and describing the path that a request takes through a system so that you can explain what happened. This task becomes extraordinarily difficult with single process monitoring tools when you're in this distributed architecture. It's no longer confined to a single process. If you try to understand this piece of the story or that piece of the story, you might be able to do it, but without the context of the remainder of the system, it's fruitless. Furthermore, it's not a straight line. It's joining and it's forking and rejoining. It's highly concurrent and it's distributed. So there's a lot of interference effects. Even if you had the signal right in front of you, there's so much noise around it that you might not be able to actually notice the thing that matters. So this is the problem that distributed tracing solves. And we did this at Google for two reasons. The good reason was that it was necessary. Google had moved to an architecture where it was impossible to tell basic stories. And it wasn't things like, we're going to make latency, the 99 percentile latency 3% faster. It was like, developer Alice has literally no idea what's happening in her system because it talks to 25 services. So it was really basic visibility had been lost. The other reason that we did it was that, at least in my case, I'd been working on ads and thought it was just excruciatingly boring, and so I left my project to work on Dapper because it was fun. So it's also admittedly like a really fun thing to do, and I think a reason that a lot of companies have adopted tracing is because it's just fun to think about, fun to work on, fun to see your system visualized in a way that makes sense and matches our own mental models of systems. I feel like at this point it would be sensible to do like a really quick demo, which always turns into this sort of situation. I'll show you our own meta monitoring. I actually sort of didn't prepare the right screen here. So this is meta monitoring of one of our own systems. What you see here is a pretty standard time series graph, best practice. By the way, if there's ever an illustration of why you should not measure average latency is that little blue line down there somewhere, and the P99 is way up here, which is the one that we're interested in. Now, measuring latency in this way is not that unusual or special these days. However, as you select a region of this graph, a tracing system is capable of showing you examples of transactions that fell into that bucket. So having selected this time window, as I'm doing that, on the bottom you see this list of links that is changing dynamically. Each one of these is a link to a trace illustrating something at that latency. So I'll open up a couple of these in new tabs. Yeah, so sure enough, these are simple traces. This is just of our own alerting system evaluating queries. You know, each one of these graphs has a shared time axis. This is probably pretty standard stuff. It looks like the Chrome Web Inspector or something. This is a simple trace. It's just one process, but it does tell us a lot. It tells us that this request has several children. The children are serialized. If we expand them, we can see some basic information about what happened. We can incorporate logging into these traces and so on. A slightly more interesting trace would be like a trace of this page view that we're doing right now. We have like some dog food stuff when I'm logged in as myself that allows me to see a trace of the page view that you just viewed. So I'll click on that link, and it's actually already collected it, which is sort of disappointing. I was hoping that I would have to fetch it. I'll get a trace of this page view now, and a tracing system is capable of potentially looking back in time, collecting information about not just the browser side of this, which is represented in blue, but the server that it's talking to and what that thing is doing. This gets more interesting. We're now dealing with two processes. You can see some fan out. If I go back to this might be, here we can see a lot of parallelism taking place. Yeah, now it has another 78 spans in this trace. So we can see a lot of parallelism. There's a bunch of SQL queries happening. We can go and look at what's actually happening in those. Anyway, the point I'm making is that complex interactions with parallelism and so forth are much easier to understand if you're able to look at a transaction log for that trace. Okay, so usually when you do this, people are like, okay, yeah, I get it, like tracing is useful. So that's not new. I mean, tracing, Dapper gets a lot of credit. For what it's worth, that paper was rejected to every conference we submitted it to, which might tell you something about the academic process and how much it values things that have no scientific contribution. And there was no scientific contribution in Dapper, let's be really clear. It's not a new idea. Like, tracing has been around since the 70s, and I think the reviewers were like, it's great that you published this, but there's nothing new here. And that's the whole point. Tracing is not new. So if tracing is useful, and I would argue that the screenshots I just showed you are useful, like, I mean, we definitely make a lot of use of them. Why isn't everyone doing it? Well, it's because instrumentation, that's why, and instrumentation has been totally broken, and I think we're just finally seeing enough, not just interest, academic interest, but genuine need because of the transition to smaller decoupled systems. We're seeing a genuine need for distributed tracing, and the bottleneck to distributed tracing has not been interest. It hasn't been tracing systems either. I mean, I think LightStep is great and everything, but Zipkin is also a totally functional tracing system that's existed for many years and is used by many companies. There are other smaller tracing systems that I also think are very high quality and are well regarded. The issue is instrumentation. And OpenTracing, in a nutshell, is trying to solve that problem for the industry in general. And I'll get into what the problem is. So distributed tracing instrumentation, which again is, I would argue, the blocking factor, it has to be explicit. Like, monkey patching software is not sustainable. Like, anyone who gets it to work, like, I challenge that person to maintain that as the thing that they instrumented changes under their feet, and like symbol names are, internal symbol names of various JavaScript packages are not part of the public API, and yet you're treating it that way. So monkey patching is not going to work. In some languages, it's just downright impossible. If you instrument code in a way that assumes you're going to use Zipkin, or assumes you're going to use LightStep, or assumes you're going to use Appdash or any number of other tracing systems, it's potentially reasonable if you're a company instrumenting your own code because you know what you're deploying. But let's say you're gRPC or your Drop Wizard or whatever your favorite framework is for building applications. It's not reasonable to assume that every one of your users uses the same tracing system. So the instrumentation code has to be decoupled from the tracing system. it needs to be consistent across platforms. I don't just mean that the libraries need to compile against each other, but the nouns and verbs need to be the same. Tracing, like in general, is an easy thing to talk about, but there are actually many different ways to represent things, and it's important that everyone's using the same set of nouns and verbs. And possibly most importantly, distributed tracing is distributed. Even if you're in a single process system, you have library X, which has strict boundaries on the top and the bottom, which calls library Y, and so on and so forth down your stack. And somehow the trace needs to propagate across those boundaries, and people need to use the same API. So if there's ever a call for standardization, this is it. Like, this is a situation that demands standardization. So OpenTracing is scoped in a very specific way to address that problem, and it has a really clear charter in terms of what it does and what it doesn't do. OpenTracing does not have any encoding format. It doesn't have any wire protocol. It doesn't specify even whether you propagate a trace ID and a span ID, which is what Dapper did and what Zipkin adopted and what every other tracing system I'm aware of in active use in industry is doing. It doesn't have anything to do with that. It really describes the semantics of what's happening in a distributed application with special focus on process boundaries and how to cross them in a way that doesn't bind you to particular transports. There's this idea of in-band trace data, so that's the data that actually gets sent along with your application request. It has to be really small, it has to be really concise. And then there's out-of-band data, that's the data that would go into Kafka and get consumed by Zipkin. There's no standardization on either one of those, and again, it doesn't matter. And the reason for that is if you look at the goals of OpenTracing, which is API consistency across platforms, keeping instrumentation dependencies small for open source projects that need to add tracing, and to avoid lock-in for both open source projects and for companies that are considering tracing vendors. Like, they shouldn't have to couple themselves to any particular company or any particular project. That's something that really should be swappable, because semantically they're all doing the same thing. OpenTracing has chosen to standardize in the areas that enable those key goals and nothing else. So it's a very tightly scoped project. This is a diagram of what I just said. I'm not really sure it's worth talking through it, but I will say that the OpenTracing API is available in many languages at this point. In each one, it's probably like a minus comments, it's probably like 50 lines of code. It's a very, very concise API, and that's the point. There's an OpenTracing contrib repository, which is starting to get libraries that bind OpenTracing to various systems, and gRPC and Finagle and some other projects are adopting OpenTracing internally as their way of being vendor neutral about tracing. But none of this depends on anything but those 50 lines of code in each language. It's a very small API. So the one way I'd think of it is that this is a project that there's no reason to fork this on GitHub. There's maybe a reason to start it, but no reason to fork it. It's not like Druid or something like that, where it's like a really powerful system that does something. OpenTracing is a standard instrumentation API. Now that we're at this metrics meetup, I wanted to kind of return to the classic fable of the blind man and the elephant, which, for those of you who don't have like a kid that you have to read stories to and everything, or if you've forgotten, is this idea that if 5 blind men or women or multi-gendered people or whatever were to come upon an elephant, one might feel the ear and think that it's this giant leaf. One might feel the leg and think it's a trunk. I mean, you can make these whatever you want. OpenTracing is a funny term. I originally called it DCP when we started this project less than a year ago, and it stood for Distributed Context Propagation, which is probably the most literal description of what's happening. We realized that no one would understand what DCP was, and distributed context propagation doesn't roll off the tongue, so we called it OpenTracing. But in retrospect, I almost regret that. It's really more of just a generic instrumentation API, and indeed it will capably generate tracing information that can be used to build distributed traces, but it can also be hooked up to your favorite logging system, or you can use OpenTracing instrumentation to extract latency metrics from any process, or you can use it to do distributed causality, or we have this feature called baggage, which I'll talk about in a minute, which is also related to distributed tracing, but is somewhat different from it. The sorts of applications for this, I think, are really manifold. Like one thing we hear a lot when we talk with companies, I don't know if you all relate to this, is that you'll have this complicated system, you have hundreds of engineers, and the various pieces of your system are talking to each other, and no one at the company, literally no one in engineering, actually knows what's deployed in production and where. And so you can use something like this to infer the graph of all of your services by looking at pure relationships. There are things like that that you can build out of this data that have nothing to do with distributed tracing per se. It's more like just a way of leveraging this stream of data that we're getting from OpenTracing. The baggage feature is also really powerful, and I've got a slide about that here. So the idea is this is just a graph showing how a request might propagate across a distributed system. Now at Google, we developed Dapper, and we spent several years building this thing. We staffed it up, had 10 or 12 people working on it, and it was designed to address problems in root cause analysis and latency analysis and so on and so forth, and was somewhat effective in doing that. After the project kind of got into maintenance mode, someone realized that the most valuable thing you could do with it was actually totally different, which is that Google spends, let's just say, billions of dollars on storage systems. It's got to be something like that. It just has to be. It's a huge amount of money. So they would like to know what's costing them money, but their storage systems have this sort of dependency graph in terms of services, where you have this big fan out at the top of all of Google services, and then at the bottom of the stack, everything comes back to Bigtable or GFS or Colossus or whatever. And so there's this diamond-shaped graph. And if you're maintaining a Bigtable cluster, you need to make sure that people don't violate their quota. Your immediate peer is not actually the group that initiated this request. So if a request comes into Gmail or something, we would often see requests in Dapper that would have literally 20 levels of depth between the front end and the ultimate storage system that was doing a disk read or something at the bottom of the stack. So your immediate peer is not Gmail, their peer is not Gmail, and so on and so forth. But somewhere at the very top of the stack was Gmail. Or you might want to know what particular feature of an application is being used that ended up costing you, this expensive disk I/O operation or something along those lines. So this paper called Pivot Tracing, which is academically relevant and scientifically novel, was published last year and won Best Paper SOSP. A really amazing paper. Seriously, anyone who's even moderately interested in this stuff should read it. It's a great paper. But they describe doing this sort of thing in a very generalized way using something called baggage. And so the idea is that, and this is getting back to my story, what happened at Google is that the Dapper project, in terms of the maintenance of the code base of the critical path of actually sending data through the distributed system, is not maintained by anyone concerned with latency. It's the team that's concerned with resource attribution at Google. That's actually the most monetarily valuable thing that came out of Dapper for Google, and it was very valuable in that they know at the level of every I/O operation in the kernel what application group initiated the request that eventually led to that. And this is on super multi-tenant systems all the way up and down the stack. So they can do very fine-grained analysis and enforcement of these sorts of quotas at that level of the stack. And what I'm trying to emphasize here is that A, this is of tremendous business value, B, it has nothing to do with developer tools, and C, it cannot work without distributed trace propagation. It doesn't have to do with distributed tracing systems in terms of the UIs that I just showed, but it's the same code path, and it's very important. And so OpenTracing has a lot of applications outside of developer tools or latency analysis. There's certainly the one I just mentioned, but there's similar applications for security, there's similar applications for compliance and other sorts of things. So there's a lot of reasons why a company might want to adopt something like this beyond just performance analysis, which is the bread and butter of the Dapper paper and what most people are pursuing with Zipkin. Anyway, yeah, so going back to this example, we can easily look at the level of a client, all we say is we have this thing called a baggage. We'll add a key value to it saying the button that the person pressed in the app was the buy button. And then we propagate a distributed trace. Because the baggage has that key value pair in it, it's propagated to the front end, which is the immediate peer, and it is in fact propagated across the entire system. Any other participant in the trace can add something else, like the front end in this case adds this experiment ID equals 57. And then the benefit of this is that at any layer of the stack, you can now group and aggregate any cost metric or any other constraint that you want to examine. You can look at the baggage, which is a full system view of what happened to this distributed request, and you can perform statistics and so on. And it's a very valuable thing. The pivot tracing paper makes it even sexier in that you can, as a user of the system, you can write a SQL query that's like the normal kind of select sum of blah 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 from your system, grouping by button or grouping by user or whatever. But there's this thing called a happens before join, where you can join activity in Cassandra on activities that happen before Cassandra in distributed requests. It then farms that query out to the distributed system, and the like in-process agents built into your system actually participate in automatically adding things to baggage as needed in order to compute the answer to this query in real time within the distributed system, where it is then farmed back to the requester in an efficient manner. And this is all done with very minimal overhead in the production system. It's really great paper. Anyway, so status report about OpenTracing. OpenTracing is deployed at a bunch of tech companies that you've heard of. I don't know what I'm allowed to say and what I'm allowed. I've signed NDAs in various places, but I think a lot of people think this makes sense from the standpoint of companies that are building applications. Open source projects have also been quite receptive to it in that it allows them to have distributed tracing support without having to bring in large dependencies or. Like, for instance, Finagle, who they're enthusiastic about OpenTracing, Finagle, just to make sure everyone knows, is Twitter's RPC system. Like, Finagle has, in their core code base, has not just Zipkin bindings, but different bindings for Zipkin on Scribe and Zipkin on Kafka. And why does an RPC system care about the transport that Zipkin is using? What possible relevance does that have to RPC? It has nothing to do with RPC. So why do they depend on it? The way it should work is they should say, okay, I'm starting a request, I'm sending a request to my peer, I'm receiving a request, I'm starting the server. That's all it should say, and that's all it needs to say. And the OpenTracing version of this instrumentation is 2 orders of magnitude less code than what they had before. So it's a good win for library owners. And then finally, it's a good thing for tracing systems in that we don't all need to try and conquer the world. We can kind of cooperate through this open tracing mechanism. And indeed, the lead maintainer for Zipkin is a friend, and he's enthusiastic about having open tracing cooperate with Zipkin, and there are now bindings from OpenTracing to Zipkin and Go and Python and Java and so on. So, and of course, my company and several other tracers have also adopted it. So the 3 communities are kind of companies, open source maintainers, tracing systems, and all 3 of them participate in kind of building up this marketplace around OpenTracing. The project started in 2016, so it's young, but there's been pretty good progress, and I expect that there's some possibility we'll be part of one of these Linux Foundation things in the next couple of months, depending on how things go. But in any case, it's definitely here to stay. If there are people who want to get involved with it, we have a website which is kind of minimal, but we'll be getting better. And I certainly welcome random emails from people, even if you're just curious and want to talk about it. Anyway, I failed in my goal of having discussion, but I left a ton of time for questions, so I hope we can do that. I'm happy to talk about anything in this presentation or related topics. So. I cannot. But I mean, it's the baggage demo per se is not, the idea of propagating it is not very interesting. The cool things are the applications of doing these rollups and aggregations and so on. So a query what I would recommend, pivot tracing, which I linked to in this thing, but it's just pivot tracing.io. They have a bunch of awesome stuff in their presentation that you can watch that's much better than any demo I would do. I would recommend watching that, and it shows the sort of power of that feature, I think, much better than I would if I tried to show you a demo right now. I can show that it propagates, but that's just sort of look, it did, But the kind of demo you'd want is something where you run a complex query over the running system or whatever. This presentation does that. And I think it's a great talk, and Jonathan, who wrote that, is super, super smart, much smarter than me, so watch his talk, it'll be better. Yeah. Well, sampling is not part of OpenTracing per se, which is another thing I'm kind of happy about. OpenTracing, in our effort to just describe semantics, doesn't need to concern itself with whether or not anything is sampled, which I really like. LightStep, since you're offering this opportunity to pitch my company, most tracing systems that I'm aware of that were deployed in production environments do some sort of upfront sampling. So in Dapper, I have this slide. This is probably as good as any. So basically, anytime you're starting a new span in your trace, which is just a timed event, you say, okay, well, do I have a parent? If you do, then you adopt the sampling decision your parent made. If you don't, you make a sampling decision and you propagate that along with the trace. So either the entire trace is sampled or the entire trace is not sampled. That's fine, except that in Dapper, the sampling rate is 1 for 1,024, and then there's actually another 10x sampling that happens later down the pipe. So it's like a very small amount of traffic that gets through. Zipkin adopted the same heuristics, and those are done for two reasons. One was to protect the process if it's very high throughput, but mostly because it's just so much data that you can't afford it. Like it's not, the value prop isn't there. If you try to throw that much data into Kafka or something, it's just operationally not worth it for a high throughput system. So with LightStep, in our view anyway, this is an unnecessary constraint to do sampling ahead of time, and our sampling decisions are all made after the fact. We have a very high throughput and low overhead place where trace data goes with like minimal syscalls and minimal I/O, and then we make sampling decisions within a minute or so of an event occurring. And that way we're able to sample things that are interesting to us rather than things that you just flip a coin. So in general with Dapper, a common complaint was that if an error occurred deep in your stack, you had a 1 in 1,000 chance of catching it. So you basically didn't see it. Whereas with LightStep, if an error occurs, we can say, oh, an error occurred, that's bad, like we're gonna sample this trace. And you sample that span, but you also sample everything that came before it. And so some sort of sampling is almost certainly necessary unless disks get a lot cheaper or something for distributed tracing systems. The question is whether you do it ahead of time or after the fact. So do you have the benefit of hindsight when you're making your sampling decisions? AppDynamics is a very valuable company that has lots of happy customers who pay them a lot of money. So I definitely don't want to throw stones. Their approach is quite different, and their initial market is also more in the monolithic side than the microservices side. So AppDynamics' approach is to, historically anyway, has been to focus on JVM systems and do black box instrumentation through Java agents. And then you write a bunch of rules that extract transactional information from JVM systems. And they attempt to also follow data across process boundaries. My understanding, which is truly incomplete, but my understanding is that it doesn't work very well if you're dealing with concurrency in a distributed system. It's just too difficult to attribute cause and effect across process boundaries using that completely no-touch instrumentation approach. For what it's worth, I got someone on Gitter asked me the other day, he's like, hey, this is amazing, like this is great, I love OpenTracing, whatever. And we were having this really nice academic discussion about it. And then it's like, so like, where do you work? He's like, I work at AppDynamics. And so I was like, okay, so I think that they see the value in this too. And I think it would be good for their product as well. Their go-to-market involved less instrumentation than a company that's trying to do microservice instrumentation. So they didn't need it. Yes, not in OpenTracing, but at Dapper we did do that with Ktrace, which Google had forked Linux kernel so long ago that was the only thing that was available. But it was successful insofar as that it worked, and it was really cool. It was unsuccessful in that Dapper had this charter not to have any observable latency overhead, and if you want to turn on kernel level tracing that of the systems that they were concerned with, which were doing tens of thousands of operations per second, it just wasn't feasible to do that without having an observable latency overhead. So it never met the Dapper criteria of being on everywhere all the time, although it was something that was turned on for particularly difficult like queuing issues, because they were having issues where network drivers were the root cause of observable user latency, and they found that using kernel tracing. I don't think there's anything fundamentally difficult about it, but it's just a hard thing. So there aren't a lot of application level developers who also feel comfortable making kernel changes and vice versa. So it's literally a problem getting the right people in the room. I think that's the hardest part about it. There's nothing technologically that's particularly hard about it. You just need to be able to look at the stack and look in the right place and so on. Yeah, that's super important. I mean, in as much as you're using distributed tracing to understand the root cause of latency, latency is something that end users observe. And if you're not observing it in the ultimate client, it's impossible to know what they're observing. Google spent a huge amount of time doing like really detailed performance work on their backends, and they would like labor, they'd have whole teams would labor for quarters to make like single-digit percentage improvements in latency. And then eventually they started measuring stuff from the client in a principled way and realized that it was totally irrelevant. I mean, it's like all the latency was in that last hop between the user and Google's data center, which led them to redesign the way that they deploy their caching layer. Essentially, they have like all these satellite data centers now just because of those experiments. And I think if you're making assumptions about performance on your client, you're almost definitely wrong. If you're not measuring it, you don't know. And it is necessary to incorporate that into the trace if you're interested in optimizing that actual user experience. Thanks a lot.